So today we're going to approach credit risk from a different perspective than we did last week. After a while, after about an hour or so, maybe 1.5 hours, we're going to see some of the issues that we developed last week come back again, but from a completely different perspective. This is what I will call a miracle when that happens. And it is a very surprising occurrence, you will see. The approach we're going to have now on credit risk is going to be as follows. The first thing we're going to, so last week I could say we were dealing with one issue, which was the issue of default. A company default is what we focused on. We looked at the probabilities of default, and then we saw how with a default probability, we could discount cash flows and do things like that. If we try to apply this to more complicated portfolios, such as derivatives or other things, it wouldn't work very well. It worked very well in a very simple situation of a deterministic cash flows. If the cash flows are stochastic, then that won't work. Today we're going to see a framework that allows for any type of financial instruments under credit risk. But this was last week, so default was last week. Okay, we will still deal with it today. In fact, we will develop other models that will help us to deal with default, but they will be very similar to the ones that we did last week. So this is almost done. The new topics that are coming up today are the concept of credit exposure and the concept of recovery. Recovery was already mentioned last week in the practical example of sovereign wealth risk. Today we'll deal with that in a slightly more structured way. I have to say, though, that what we're going to do today is very, very difficult. There isn't a theory that just solves it for you in a nice way, like the fundamental theorem of asset pricing or something like that. A lot of what we're doing here is theories developed by the industry to address the problems of the industry. And they do to an extent, and today we'll learn what they do, what they don't, when these things work and what they don't. And there's going to be two objects of desire for us. One is going to be the calculation of the expected loss, something that somehow already came up last week, and one thing which did not come up last week, which is the concept of unexpected loss, which will lead to the regulatory frameworks for credit economic capital. When a bank has a certain credit risk profile, then they are required to keep a certain amount of assets with the central bank as regulatory capital in case on the one hand, in case the bank falls under, but also in case that or somehow to discourage risk taking on the part of the bank. And that is what credit VaR and some other measures of unexpected loss will do for us. Expected loss will be able to do that in the realm of probabilities and expectation. The other one is going to be different. Okay, and these are the topics that we will discuss today. All right, so I'm going to start with credit exposure. The definition of credit exposure is the largest amount of money you can lose in the case of default, with a certain level of confidence. The largest amount in the case of default is a number that in certain situations could be infinity, because cash flows are stochastic, they could grow infinitely big. So we need to set a confidence interval to make this a number finite. It's a quantile. It's a quantile over a lifespan of a financial product. I have an example here. Imagine that this would be the 95 percentile or the 99 percentile of the value of the Goodrich swap. We saw the Goodrich swap last week. This is a swap that when you receive a payment, the credit exposure drops because the money at risk, so to speak, has fallen. You've already received payment, but as time goes by, this amount of money you could lose could increase. Do you see where the increase comes from? The increase comes from the uncertainty of where interest rates could move. I remind you that in the case of that swap, rates could move one way or the other. If rates move down, our credit exposure goes up. Okay, and since we don't know where interest rates are going to go, we will see the credit exposure increase for a period of time, and then it will decrease when a payment is made. So these decreases that you see here are the decreases when swap payments occur. And this is the perspective on the future exposure that we have now. And this is a quantile. Okay, the largest amount of money we can lose is infinity, because if rates, well, maybe not infinity, because in this case, we lose when, on the Goodrich case, we lose when rates go to zero. So the most we could lose is 55 million. On the Rabobank, the maximum we could lose was infinity. If rates go to infinity, we will lose infinity. Note one thing, we discussed last week that Rabobank was AAA rated, so the credit risk was not an issue there. Note that in my definition of credit exposure, I don't care who my counterparty is. The definition of credit exposure is independent of my counterparty, independent on their credit quality. It is, strictly speaking, only the largest amount of money we can lose. So it is independent of the counterparty. See, the counterparty is not there. It's a conditional amount of money we can lose. If it defaults, this is how much money we can lose. So the credit exposure calculation here would apply to both the Goodrich swap as well as the Rabobank swap. Okay, so this is very important. Okay, if you go here, we have a credit exposure, a recovery, and default. So default, this is what makes Goodrich and Rabobank different. But when it comes to credit exposure, turns out that the credit exposure of the Rabobank part of the swap is higher than the credit exposure on the Goodrich part of the swap. Why? Because in the Goodrich part of the swap, we stand to lose money. Our exposure increases when rates go down. They can only go down to zero. So the exposure will be limited at $55 million. In the case of Rabobank, rates could go to infinity, and then the exposure can get as large as you want. This is very important. This is how we're going to be approaching credit risk today. There's a comment in the chat by Daniel. So since we're dealing with confidence, yes, but confidence interval is not for the credit, it's for the market aspect of that. Okay, so interest rates could move up or down and with a certain probability, and interest rates is what causes this. So this is from a market probability perspective. Okay, that's a good question, Daniel. Has nothing to do with default. Credit exposure has nothing to do with default. It has to do with the value of the portfolio that I have in my books. So again, making a reference to the Rabobank swap, the credit exposure of Rabobank is much higher than the credit exposure of Goodrich. Because in the case of Goodrich, our credit exposure increases when rates go down. In the case of Rabobank, they increase when rates go up. And there is further direction to go up than to go down for interest rates. Okay, is that clear? And it is over time, okay? It is over time. It is not at a specific point in time. It's usually done over time, which means that at the highest possible value would, in this case, would all be for the 99 percentile, maybe, I don't know. That will be my number. That will be my exposure, my credit exposure. Okay. And there we go. All right, so that's that. The recovery rate is the other topic that we introduced last week. Now I'm going to spend a bit more time telling you how that works. When default occurs, a portion of the value of the portfolio can usually be recovered. So in the case of Silicon Valley Bank, I don't know what's going to happen with it, what kind of bankruptcy proceedings there may be or what. I don't know. But there will be creditors to the bank, entities that the bank owes money to. When someone defaults and does not pay, usually, as we discussed, you don't lose everything. And now there's going to be some sort of a competition, some sort of a legally defined proceeding that will give the creditors some partial payment of what they're owed. We express this in two terms. One is the recovery rate, which represents the percentage value that you would recover. So 80%, 50%, 60% of what is owed to you, you will recover. And that's one. And then the one which is actually also used even more often is the loss given default, which is exactly the opposite. 1 minus loss given default. So it says, does government insured coverage given default affect recovery rate, or does recovery rate exclude that? Okay, so this is a complicated question that you're asking because, for example, in the case of a bank, depositors are covered. They are insured by the FDIC in the United States. And that will be somehow guaranteed by the government. So the recovery rate there is probably going to be 100%. This is typically not considered a part of the credit equation. In other words, a depositor is not considered to be a creditor. Bank deposits are regulated differently from commercial transactions. So in the case of depositors of a bank, they would get their money back, typically all of it, according to certain rules put up by the FDIC. Where credit risk typically applies is to bondholders, for example, and entities who either bought bonds of the bank or lend money to the bank. Depositors are regulated differently. I think that was your question, Daniel. Yeah? Depositors, there's some conditions, say accounts of up to $100,000, this and that. There's some conditions for deposits which will make deposits not be part of this credit risk analysis. This credit risk analysis is for contracts which are regulated commercially, not through, in this case, banking insurance. So recovery and loss given default. They are quantities which are opposite to each other. Loss given default is more related to credit risk, and that's the one that we're going to be using when we write our credit loss equations. But this is very simple. Now, this is an important consideration here because this is an unknown. We don't really know in the case of a bankruptcy or default what is the percentage that will be recovered. What I have here is a table. It was done by Altman is the big name here in this thing, Lieberman and these guys. These are two. This is the one that I'm most familiar with. Okay, but there are two studies. And in this study, they're very old. These studies are from very, very early on. I still use them because it's not that I care that these numbers are correct or even up to date. What I care is about the thinking that goes into this. And this is actually the part that I'm most interested in. The numbers I'm less interested in. I'm more interested in the left column. What does it say here? It says seniority class. And then it says senior secured, senior unsecured, senior subordinated, junior subordinated. What do all these things mean? It's important to know. So senior means you get paid before junior. Okay, senior gets paid before junior, so you are ahead in that curve. Secured versus unsecured means that there is some security, some collateral applied to that. So unsecured has no collateral, secured has collateral. And subordinated means that you are at the end of the line when it comes to bondholders. And then there's another category which is junior subordinated. So that's two categories for subordination: junior and plain subordination, which are always at the end of the line when it comes to collecting their payments. And they have senior subordinated, senior unsecured, and senior secured. So senior secured to get paid first. Senior secured get paid first. And you can see here that when you look at the used 85 cases for their study, their average recovery was 50% with a standard deviation of 23. That's in the Altman study. Okay, I guess very similar to the study of Lieberman, very similar. And then as you go down in the senior unsecured, senior subordinated, then you can see that the recovery rate drops. The junior subordinated, they typically get nothing, according to this analysis. Well, that's what I interpret this sign to be. Here is a very small percentage that they recover. Okay, so when a company, like in this case Silicon Valley Bank, when they have a creditor, the creditors are organized into what's called the capital structure of the firm. Not everybody has the same rights to the assets of the firm in the case of bankruptcy. Is this clear? Okay, good. So how do you turn this into a model? You can do two things. First, what we'll do in the first half of today, which is we'll just use a number, a recovery rate, which is either a number or a very simple random variable. And in the second half of today, what we will do something different. When we introduce the Merton model, we will see that the Merton model already comes with a recovery rate model built into it. It's different from this. It is a little bit academic, but you will see that there's some very good connections between the two. We will see that later today. Okay, so this is the recovery rate. That's how it works. Now, when it comes to default, there's not very much to add to what we did last week. Last week, we were very thorough on the concept of default. We were not thorough on the concept of credit loss, but we were thorough on the concept of default. We saw a Markov model for expressing default, first 2 stage, then 8 stage, which are the transition probability matrix, all of that. Today, we're going to do almost the same. There's only one new concept I'm going to introduce, which is called the default process. The default process is a process which is 0 until you become insolvent, and then it's 1. Okay, so at the time you become insolvent, it jumps from 0 to 1. So it's a stochastic process. It's a stochastic process. And the probability of default is the expectation of this stochastic process. This stochastic process will have a random variable at each point in future time, and the expectation of that random variable at that point in time, the marginal random variable, if you want, at that point in time, or the conditional random value at that point in time, will give us the expected default. So it's the same thing we defined last week. I'm just going into the process whose expectation will give rise to the probability of default, which is what we studied last week. All right, good. So this creates the 3 building blocks that we will use to define credit loss, which is defined as this. Credit loss is a super stochastic process, which is the product of 3 stochastic processes. One is the default process itself. The other one is the credit exposure as a quantile function that, of course, may change over time. And then the loss given default as a random a process also, of which we know very little about except some historical studies. That's how we approach this. And I say this, it's a super stochastic process because it's the product of 3 stochastic processes, each of which is a function of different random variable. Or sorry, it's a function of different factors. And what's important here is that the default process depends exclusively on the credit quality of my counterparty. Credit exposure depends exclusively on the market risk of the instrument of portfolio. Like I said earlier, you would do this for Rabobank or Goodrich. It doesn't matter which one is better. And then the loss given default is a number which is perhaps the hardest to understand, which is what will happen in the case of default. How much money do you get back? How do you analyze your particular senior secured security versus the senior unsecured, and so on and so forth? Okay, so these are processes that we might multiply together, which depend on completely different factors. So this is a definition which, as it stands, it's not very practical in itself. We'll make it practical by making assumptions and adapting this to specific situations. But is this understood? This is a landmark for the class today. The definition of credit loss. It's a random process. It's not a number. It's a random process, depending on lots of very weird random variables. And when you have, that's a credit loss with a single counterparty. When you have several counterparties, the credit loss is additive. It's the addition of the credit loss for all the different counterparties. This part is not going to be, there's no additional complication to go from one to several credit counterparties, except when it comes to the simulation. There's going to be one approach to doing this with simulations. And of course, with simulations between one or a million counterparties, the simulation will become very challenging. We'll see that. Now, once we have the credit loss process, what we do now is think about the credit loss distribution at a given point in time. So now we specify a point in time, say a year, and in a year, this process will give rise to a credit loss distribution. That will be a random variable, okay? And this random variable is, how can I say, it's unusual. It's unusual. First of all, it's completely asymmetric. Credit loss does not account for credit gains. So it already lives on the loss part of the distribution. Okay, and the positive axis is typically considered to be the part about the loss part of the distribution. So that's for the credit loss distribution itself. The first attempt we will make at understanding this distribution is to parameterize it. And in parameterizing it, we're going to look at the mean, which will give rise to the expected loss. Expected loss is a term, and it refers to the mean, okay? You can say, well, it's the expectation of the loss, so that terminology is to be expected. Maybe. But note that there's an unexpected loss. The unexpected loss makes a reference to the standard deviation. And that, again, is a terminology which is perhaps an unexpected terminology that you call unexpected loss, the standard deviation. Why is the standard deviation considered to be the unexpected loss? I will explain with one example. All right. So this is the way we're going to start to parameterize this distribution. As you can imagine, this distribution, the mu may have a meaning, but the sigma is probably not going to have a very deep meaning. It will have some meaning for sure, but this distribution is very asymmetric and very likely has very fat tails over here. So the standard deviation will typically underestimate the bad things that could happen from a credit loss perspective. And we will see that. We will see that explicitly in some examples that will come up later. But is this understood? Very simple. Mu and sigma. Back to mu and sigma. Not very hard. Okay? All right. So in doing this, it's important to have a mean of understanding risk which goes beyond the standard deviation. The standard deviation will typically tend to underestimate risk. The first measure of risk that we're going to consider here is the worst credit loss. And the worst credit loss refers to the largest amount of money I can lose in the case of a default within a certain period of time and with a certain confidence interval. So two parameters, period of time and confidence interval. For example, 95%, for example, a year. That's called the worst credit loss. So worst credit loss is a quantile. It's a quantile. And from the perspective of our distribution, it could be somewhere there. Okay? If this area here equals to your confidence interval, say 5% or 1% or whatever the number is. Okay? We saw this as the definition of value at risk, remember, when we saw market risk 2 weeks ago? But now we don't call it credit value at risk. We call it worst credit loss because the credit value at risk is reserved for something different. The credit value at risk is the worst credit loss minus the expected credit loss over the same time horizon and over the same or with the same confidence interval. So why, this is a question, why is the credit VAR the quantile minus the expected credit loss? Why is that? In the case of default, I will lose the worst credit loss. How come my credit VAR is the worst credit loss minus the expected loss? The reason is for something which would be called risk accounting. The thing is that you don't account for the expected credit loss and the unexpected credit loss in the same way. As we will see, there's an example that will make it quite clear, I think. When you do a transaction, the expected credit loss is priced into the transaction and is usually translated into a type of a discount that you obtain. So you get an economic gain. The expected credit loss typically gives rise to an immediate gain in your transaction. That's why it's not considered as part of the regulatory capital, which is our objective with this. So in other words, this is a good measure of risk, and this will be a very good measure of regulatory capital. Okay? And the function of regulatory capital and the measure of the objective of a risk measure are different. In the risk measure, you want to know how much money you can lose. In the case of regulatory capital, you want to know how much money you should require someone to put up. The idea is that the expected loss has already been charged somehow, so it's not going to be part of the regulatory capital calculation. All right. So examples, what does this mean? If the 95% worst credit loss of a $5 million portfolio is what is reported, that means that this portfolio has a probability of 5% of losing more than $5 million. And if what is reported as the credit VAR of a portfolio is $5 million, that means that there is a 5% chance that this a 5% chance you will lose more than $5 million plus the expected credit loss over the same time horizon. That's what these quantile functions mean, okay? I hope it's clear. All right. And the way that credit risk and the way that risk management is done within an organization, like especially a bank, is there is two aspects to that. One is the credit reserves, which are the ones that we do through expected losses. If you know you're going to be, you are expected to lose a certain amount of money, then that you charge ahead of time, or for example, in the case of a mortgage or a swap, as monthly payments, and this goes into the credit reserves. You reserve that to make up for potential losses. It is the expected loss, so you expect to use it. This is not money that you want to spend. This is money that we want to keep. It's a reserve because you expect to have to use it, okay? This is the amount of money you expect to lose. That's what's called a credit reserve or expected losses. And capital or regulatory capital refers to the unexpected losses. This is what could happen over and above the expectation of losses. From this perspective, a bank works like an insurance company. An insurance company, they would, if they sell you car insurance or fire insurance, they would calculate the premium of that based on the expectation, and then you get charged the premium that satisfies that expectation plus a profit margin. In the financial industry, things are done like that on this side, but this is something additional. And the reason is that insurance companies can afford to have very diversified portfolios, so the unexpected loss is typically very small. In banks, when you do 1, 2, 3 transactions, you don't have enough diversification. You typically don't. So the considerations of risk are more important, and you have to somehow charge additional. The benefits of diversification that insurance companies have for insurance products is not present when you're doing credit transactions in the financial sector. There aren't enough of them so that the expected loss is all you need. That's the difference between a financial transaction of risk transfer from an insurance policy. Is this clear? This is very important, a very important distinction between the insurance sector and the banking sector. Okay, I think it is. Great. So netting is an old concept. It used to be that netting agreements were not in place, and you could be in the situation, very strange situation, where someone defaults, they owe you money, but you owe them a little bit of money. Maybe they owe you more than you owe them, right? And then without a netting agreement, they're not going to pay you because they are in default, but you still have to pay them what you owe them. Okay? So, netting agreements are now common, and typically you calculate the net exposure before you determine if you're a debitor or a creditor. Okay, so Chris is asking, what is the Markovitch theory referring to? Sorry, the Markovitch theory, I have it here because I always think that everybody knows, but actually you don't. I'll tell you what the Markovitch theory is next week. Okay, that's coming next week. Yeah. Okay, so here, Chris. So if I have a house and I can take a line of credit on it, is that a credit reserve? Okay. Hold on. So you have a house and you take a line of credit on the house. So is that a credit reserve? Okay, so what's your credit transaction here? It looks to me that you don't have, again, if your perspective, okay, in this example you're telling me here is you have a house, the house is yours, and now you're taking a line of credit on it. So no one owes you money. So your credit exposure is 0. You don't have any expected or unexpected losses. Chris, is that clear? What I'm talking about here refers to a credit transaction. If you borrow money, say on a house, you don't have a credit transaction. The bank will have a credit transaction. The bank will have a credit transaction. And so let me finish. So the bank will have a credit transaction with you, and then it makes a difference if it's, say, a personal unsecured line of credit, in which case the bank has, well, they can go after you and whatever you happen to own. Maybe the house, maybe not the house. Maybe you sell the house, and then that's, or they have the house as collateral, in which case it'll be a mortgage. So for the case of the bank, when you have a collateral, that's not a credit reserve. That's something else. A credit reserve would be what the bank does, what the bank keeps aside, because let's say you have a poor credit, then they charge you more for that loan because of that credit rating that you have. That they charge you will go into a credit reserve, because this is money that they don't think they're making money on that. The fact that they charge you more percent to you than to someone with a lot of money or with a very good credit, the fact that they charge you that 1% more is not because they think they're making 1%. That 1% goes into a credit reserve because they expect to lose it. They expect to use that 1% to pay for the losses of you or someone else within the credit portfolio. Okay? Is that clear? Now, If you are now taking a credit risk position with someone else, and I think that's what your next question may refer to, then what you charge for that transaction, so, well, I don't trust you, so, I want to charge you more. Again, that's not collateral. The collateral is not yours. Okay, the collateral is something you will get if there is default, but it's not yours. The house does not belong to the bank, for example. So it's not a credit reserve. It's not theirs. Okay, but if you do a transaction and you charge someone more, what you charge more because of the credit risk is money you're going to lose. Okay, it's not money that you cannot call that profit. It's lost money. You're just charging that ahead of time because you expect these losses to actually happen. Is that clear, Chris? These are good questions. Okay, everybody should understand these answers. This is how credit works. For example, a common misconception is to think that when you have a mortgage, the house belongs to the bank. No, it does not. The bank can only take the house if you don't pay. Okay. All right. Well, I think it's clear. If not, ask me again. Okay. These are important topics. All right. Now, so in our context, then the expected credit loss will be the expectation of my super stochastic process, which depends on many different factors, but I just multiply them together, and then this is the expectation of my multi-factor credit situation, where that will be the joint probability of density function of all of these things, and that's it. This is how we apply statistics to what we're doing here now. This is a monster. This thing we have in front of us is a monster. You could simulate this, but even to simulate this, we need to start to understand a few things. The first thing I want to say is, if all three events are independent, if the exposure that I have with the counterparty is independent of the default probability of that counterparty and independent on the expected severity of my counterparty, which is the worst credit loss, or the expectation of the worst credit loss. If all of these are independent, then the expected credit loss will be the product of all three. And you can say, well, yeah, they are independent. The probability of default and the portfolio are different things, who cares? And they are independent to each other. And of course, the severity, I don't know what the expectation is going to be for the recovery rate. So yes, let's say that they're all three independent, right? Then you multiply the expectation of that, the expectation of that, and the expectation of that. What is this? That's what we call the probability of default last week. So that's the probability of default, P, times, what is that? That's the expected credit exposure. It's the expected worst value of the portfolio. It's as if my portfolio would somehow default at the worst possible time, the expectation of what that big default event can be. So that's a value. And then the expected severity, you can take, for example, if they're independent, you can go at the Altman study and then use that number, because that's what it is. It's the expectation of it. Okay? So you just multiply these numbers, and that's what this would be in the case of independence. So it's not very difficult. This part is not very difficult, is it? The expected credit loss under independence is not very difficult. So maybe that's a good way to start. And now what I have here is, I want to make sure that you understand this very well. And I have two exercises for you to do. I want you to do them. Okay? Not me, you. I want to give you a few minutes. And the first one you may not do, you may be scratching your head, but the second you should be able to do, because it's very similar, and I would have given you the solution to the first one already. And the first is something that happens frequently in mortgages, in commercial mortgages especially. So I want you to think that you are a bank and you have a commercial mortgage. Say the shopping mall is the collateral. And assume that the mortgage is $100 million. So that's the exposure. It doesn't go up, it doesn't go down. It's $100 million. That's what you lend, and that's if something happens, that's what you will lose. All right. But then we're going to have a probability of default of 20% and a recovery rate of 50%, 50. What's your recovery rate? If they don't pay, you take the shopping mall and then you sell it to someone else and you sell it half price. You think you will sell it half price. Half price should not be a problem selling that shopping mall, right? You understand what we're thinking? Yeah. Now, to make the problem more interesting, I'm going to say that the probability of default is 20%, but I'm going to introduce a standard deviation on the probability of default of 20%. That means that the probability of default could rise to 30% or decrease to 10%. We don't know. And then I'm going to say that the expected recovery of 50 is because I could recover 60% or 40%. Let's say that the shopping mall that defaults is in very good shape. It's all great. Everything is working. You may even have some tenants who pay rent and everything. So then I can sell it for more money, right? If on the other hand, everything is broken and there's leaks in the bathrooms and who knows what, then it'll be more expensive. I'll have to sell it cheaper. That's why I introduced the standard deviation of 10%. Do you understand the commercial reason for these numbers? Do you understand the commercial reason for these numbers? The 100 million is fixed. The probability of default could oscillate up and down. And the recovery could also oscillate up and down. Okay, so in that context, I ask you to do the calculation. This is actually, I don't know, you may be surprised that you can actually calculate this. You can calculate this. Things are not as difficult as they may have seemed when you write them in big abstract notation. So I want you to do two things. I want you to calculate the expected credit loss, assuming all these three variables are independent to each other, and I want you to calculate the expected credit loss assuming a negative 50 correlation between the default probability and the recovery rate. Now, before you start calculating this, let me mention why a negative correlation between the probability and the recovery rate makes commercial sense. Typically, if you have a shopping mall, say the Eaton Center, okay, imagine the Eaton Center. I mean, I don't think the Eaton Center will default. They are owned by Cadillac Fairview, which is owned by Entire Teachers Pension Plan. I don't think they will default, but let's say that they can default. They don't default from today to tomorrow. Like, oh my God, I have to pay, my mortgage payment to the bank and I don't have money or something. This is unlikely to occur. Typically, for commercial mortgages, these things take a long time to occur. So by the time the Eaton Center has defaulted, they have cut down maintenance and the whole place is a mess. Okay, maybe they've lost some tenants, maybe some windows are broken, they're boarded up with. It just doesn't look good. So the probability of default is typically correlated to the expected recovery. Okay, when something is more likely to default, the recovery is typically less. That's why I introduced this negative correlation here. That's the reason. This is the commercial reason. This is how commercial mortgages typically work. They're very different from residential mortgages. In residential mortgages, this typically doesn't happen. But in commercial mortgages, it does. And I should say one more thing. This is just general knowledge for you. You know Lehman Brothers, the default of Lehman Brothers in 2008? You probably know that it was their mortgage book that brought them down. What's your guess? It was the commercial or the residential mortgage book that brought them down? Commercial. Yeah, commercial. Okay. Commercial mortgages are different from residential. They're riskier. And actually, this is a very good example that will help you understand that. And this is something that you can do with pencil and paper. You only need pencil. You don't need Python or a computer. You can do this with pencil and paper. Okay. Now, I can tell you the answer, but something tells me, well, I know from experience that if I tell you the answer, you'll say, okay, yeah, I got it. And I prefer that you try, because then if I give it to you after, say, 5 minutes of you trying, you'll react differently to the solution. Okay, so I'm going to give you actually give you 4 minutes to attempt it until 12:20. And then I give you the answer. I know that you can read the answer by turning the page in the presentation. I know that. This is not a test. I want you to try to do this, to see what you learn by attempting to do this. Let's see what ideas you come up with. Okay, so in 4 minutes, we resume. You try this on your own. I'm going to shut up. So I'm interested in not whether you got it or not. I'm interested in what do you do? Is this something that you know what to do? Was it clear? Any comments? I'll give you the solution. The solution will do it in 1 minute. Okay, so let me show you the solution. So the first thing that I need to do, I need to somehow model this idea of the probability of default being 20%, standard deviation of 10, and recovery rate of 50%, standard deviation of 10. So what I'm going to do is I'm going to create two correlated coins. By the way, I mean, I hope this is obvious, right? If we assume independence, the answer is 10 million, because I didn't give you any other choice. It's just a multiplication of the expectations. Everybody knows that. 100 million times 20% times 50% is 10 million. So there's no question on that. So we only need to look into what happens with assumption 2, assuming a 50% correlation. In that case, what I need to do is model the correlation. And I'm going to model the correlation in the simplest way that I can, which is with two correlated coins. So I'm going to take two correlated coins. Well, this is the answer. So two correlated coins that will be consistent with this somehow tree-based approach to what we're doing. And for that, what I do is I create two correlated coins. And what I need to know, I know the probability is 50-50, okay, for each coin. But the question is, what is the joint probabilities? What are the joint probabilities? What is the probability of, for example, event that both go up, that both go down, or that they go down up, or actually that's the same, or up down? You know, what are these probabilities? These are four unknowns that I have. Now, these four unknowns, because of the loss of probability, satisfy these marginal probability constraints. Those are obvious. And the correlation equation means this. This is what the correlation equation means. Is that clear to everybody? That's the correlation between my default and recovery events. Minus 50% probability, minus 50% correlation of those events happening corresponds to exactly this equation I have here. Is that clear? Good. So the solution to the system of equations is this here. There is a 12.5% probability that they both go up and down at the same time because they're negatively correlated. And there is a 37.5% down that they do something which is different. Yeah? 37.5%. So these are the numbers. So with these numbers, what I do, I go into my expected loss calculation, okay, and I take into account my 2-factor times 2-factor event space, so that's 4 factors. And each of these 4-factor space, what I do is I just multiply the loss given default, not the recovery rate, the loss given default times the probability of default, and then I get the answer, which is 10.5 million. Okay. Now, what is that clear? Now you can model this differently. You can simulate. You can do, get some Python code and simulate something. Yeah, you can do that too. But I like this simple approach where in 1 minute we can actually do it with pencil and paper. Okay. Once you know this, then you can go into computer mode. But until then, we do it like this. Okay. Any questions on this? Well, there's some interpretation which is interesting, which is we now know that the commercial mortgage Commercial mortgages, they all have this. Okay, in fact, the correlation is probably even higher than 50%. So basically, commercial mortgages have a way of increasing the probably the expected credit loss. They have a way of increasing the expected credit loss. So that's why commercial mortgages are bad. Sorry, they're worse than residential mortgages. They are riskier than residential mortgages. This is the reason. This example we do here in 1 minute is the reason. Someone says confused about LDG. Yeah, you should not be. Maybe here in this calculation, you just have to make sure that here maybe you would have written 0.4. That's the recovery rate. But see, the recovery rate is not what goes into the calculation of the credit loss. Is 1 minus the recovery rate, what we call loss given default. Is that what you're asking, Yuja? Yeah. So the 40% recovery rate means 60% loss given default. And same with all of the others. Okay. All right. Now this thing we did here is interesting. It's very simple. You could even say, well, maybe this is not probability. This is something else. The spirit should be clear, and this is the type of dexterity I want you to have when you deal with these things. Okay. This approach works, and it's something that you need to know. I have here another example, which is the Goodrich and the Morgan Trust. And it is exactly what we discussed at the beginning of the swap discussion last week. I told you why that swap was considered to be a very interesting swap with a lower credit profile than normal, or that you would normally otherwise think. And it was because of the relationship between Goodrich and its credit profile and the direction of interest rates and their impact on the credit exposure of that portfolio. So I've modeled this in exactly the same way as the previous exercise, and I still also want you to do it. I just want to give you 5 minutes to try it, and I'll read it first to you. So here I'm assuming a total exposure of $10 million with a standard deviation of 50%. It could become 15 million or 5 million. I assume a default rate averaging 10% with a 3% standard deviation, so it could be as low as 7 or as high as 13, and the recovery is fixed at 50%. I want you to calculate the expected credit loss, assuming independence, and if I want you to calculate the expected credit loss, assuming a negative correlation of 50%, which we call Y. And what are the answers? I know that the expected credit loss is clear. It's always $500,000. There's no other choice. That's okay. That's the easy one. So which one is the right one here? Which one is it? And as before, you can argue that it cannot be that. And here we expect the expected credit loss to be lower, right? So it should not be that. That cannot be, because then that's higher. It cannot be. So is that or is that? Which one is it? And for that you have to do the calculation yourselves. Obviously, that's the right one, right? I think everybody knows. But please do the calculation. I want to give you 4 minutes for that. You don't need to calculate the probabilities of the coins. You already have that. You just need to do the calculation of the different events. And so it's say 12:29. Let's say by 12:33, 4 minutes. Okay, I think we can come back. I assume this was easier than the previous one, or at least you knew exactly what to do. I don't know if there are any questions. I'm going to just go right to the answer. That's, again, it's either this, the other, C or D cannot be. And we do the same calculation as before, taking into account the 4 things that could happen, the 4 joint events. We know their probabilities. That's the answer. Okay? And so indeed we were right. And now we can quantify how right we were last week when we argued as Salomon Brothers argued in 1983, that this credit risk profile is lower than it seems. You can, I mean, the numbers are not very realistic. The actual reduction is greater than what we see here, but that was not my objective. My objective is that you understand that there is a reduction, and the reduction is actually in the right way. It's in the right direction. Okay. All right. This is an interesting question. I want to go through. I will give you the answer, but these are some of these problems that I give you here that I want you to try on your own. So this is a problem from the FRM exam of 1998. I have access to some of the old questions. I don't have access to the new ones, but I'm not interested in the new ones. I'm interested in interesting questions anyway. So here's calculate the 1 year expected loss of a $100 million portfolio comprising 10 B-rated issuers. Assume the 1 year probability of default of each issuer is 6% and the recovery rate for each issuer is 40%. So this question is almost not a question of credit risk. It's just it's an English exam. You just need to understand everything that's there, because the answer is just a straightforward multiplication of this, right? That's the answer. It's just that you have to be careful that you don't multiply be careful, don't multiply by the recovery rate, which is the number given. You have to multiply by the loss given default, which is 1 minus the recovery rate, which is 60%, not 40%. Then the 6% probability of default is there, and that's the answer, $3.6 million. That's the expected loss of that bond portfolio. I assume this is clear. Yes, no one has a question on that? Okay, so if this is clear, then I'm going to ask you another question, which is, this is my question. What is the unexpected loss of the same portfolio? Unexpected loss. Now, to ask or to do the unexpected loss, I need to know the dependence between the different defaults between the different entities here. And I give you three choices. One is that the correlation is 100%. In other words, the bonds are exactly the same or given by the same issuer. The other is that correlations are 0%. So they are given by issuers in different sectors, different countries, nothing to do with each other. Or 50% because, well, let's say they are in the same sector. So these are the three variants that I ask you. Let me do them, and I'm going to do them. Well, first of all, if they are the same issuer, that's the easiest. I'll do that one first. If they are the same issuer, then the probability is very simple. It's just the same. It's just the standard deviation of each one of them multiplied by. Sorry, let me just see. If it's so, I do the calculation of this. I have my expected loss. That's my largest loss, or the event where I lose everything. Oh, there we go. Someone is asking me to show the question again. You want to try this on your own? That's the question, right? So a portfolio of 10 bonds with different correlation numbers between them. So this is the first one. This is when I have my 10 bonds are the same, so they all default at the same time or not. I have the probabilities of default here, so I have the unexpected loss equal to $14 million. Unexpected loss defined by the standard deviation, $14 million. Okay? If the the correlation is 0, as you know, the standard deviation does not grow linearly. It grows like the square root of the number of them. So each of them has a $1.4 million standard deviation. So $1.4 million times the square root of 10 gives me $5 million roughly. So we can see that the unexpected loss has dropped from 14 million to 5 million, about a third. And then if the correlation is something different, so neither 0 nor 100, then you just expand out the variables that we're dealing with. And these are the loss variables, okay? Not the bond values, the loss variables. The loss variables are given by these. You just expand the variance of each of them, and you have the diagonal and the off-diagonal part. The diagonal is easy. We did it already. Is the part where only the information of each of the issuers is included. This is the part which is new, where the correlation enters here. And then the answer is 110, and therefore the square root of 110 is the right answer. Whatever the number is, 3.5 or something. Sorry, 3.5, no. What am I talking about? It's like 10.5 maybe, or something like that. Just a little bit bigger than 10. So that gives us three answers: 14 million full correlation, 5 million no correlation, and about 10 million for intermediate correlation. That's how you do this. I'm assuming these problems pose no challenge once you understand what we're doing, and I think you understand, right? Okay. Exactly. So 2 is the one with the lowest risk. Obviously, 0 correlation is the one with the lowest risk. Great. Okay, so I have more questions here. I'm just going to go through them. I want to ignore them. Okay, you can read them on your own. Please do them. I think you have similar questions to these in the Top Hat book for those of you who purchased it. And I just want to go to, I want to do an example. I have some theories here about the expected and unexpected loss over time, but I want to do this through an example. There's a bond trade that I want to do. And this bond trade that we're going to do is going to be is a real, well, not real, it's not a real bond trade. But a lot of the real issues that occur when you're trading bonds, defaultable bonds, or actually when you're doing defaultable trades of any type, not just bonds, these things come up. So what I want to do this, but I want to do this after a break. I need everybody, including myself, to be very fresh for this exercise. We're going to do a real trade. And I advise you that to do this trade, I'm going to need 2 volunteers to trade with me. So if someone is willing to volunteer to trade with me, please let me know, and then we will do it that way. Okay? So we're going to take now a 15-minute break. I'm going to have a coffee. Maybe you're going to have a tea or coffee or something, but come back fresh, okay? We need to do something very intense when you come back. So we'll come back at 12:55. Great. So this is what I'm going to do now. I have an example of a defaultable bond here, and I'm going to do several things with it. I'm going to calculate the credit profile of the bond. I'm going to calculate the expected and unexpected loss, and I'm going to, most importantly, I'm going to explain to you how this bond would be traded if you are a bank who's a regulated entity, that every time it takes risks, it has to report it to the regulators or the authorities. And I want to then see how a hedge fund would do this. A hedge fund is unregulated. They can take risk, and it's only their own investors who may suffer if something goes bad. And for that, I would like to have 2 volunteers to trade. I already have one. Chris has volunteered to trade because you were the first you can pick to be either a hedge fund or a bank. It's whatever you prefer, Chris. And I would like to ask if someone else wants to be my trader on this. Do I have another volunteer? You don't have to do anything, but I'll refer to you by name. It's just easier to explain the differences Chris, what's your preference? You prefer to be a bank or a hedge fund? Daniel will volunteer. So Chris will be the hedge fund. So Daniel will be the bank. Okay, not Silicon Valley, a different one. Okay, great. So let's we'll do that. All right, we're going to trade, and this is the bond we're going to trade. This is a bond which is there for sale. It's a bond issued by a default-prone counterparty that has actually a probability of default equal to 7% per year. And the bond is a very simple bond. It only has two coupon payments, no principal. It pays $5 coupons every 2 years. So at the end of year 2 and at the end of year 4, it pays $5 coupons each, $10 total, and that's the end of it. It's a 4-year bond. And we're going to do several things with this bond. The first thing that I want to do is I want to explain what is the credit characteristics of this bond. For that, I'm going to do the following thing. I'm going to have here, we are now here, the bond is solvent, okay, and the bond has every year it could stay solvent or default. Next year it can stay solvent or default. It can stay solvent or default. This is a Markov process, okay? This is the same Markov process we saw yesterday. Yes, question? Chris? Or someone is asking a question? Sorry, I could hear some noise. I thought it was a question. Okay, great. So this is the Markov process for that bond. Every year it could default or stay solvent. And we know the probabilities. The probabilities are, as we saw last week, we're going to assume they're constant, they don't change. Later today, I have only 1 hour left. I'm going to have to speed up a little bit. But not in this example. This example I want to do slowly. I want everybody to understand it. I'll speed up in the end, but not now. Later we will see that we could make the probabilities time dependent and this and that. There's other, but not now. Now we're going to do it like this, all right? And these are the probabilities. We know it's 7% on year 1, but then on year 2, the probability that it's solvent is 86.5%, and in year 3 is 80%, and in year 4 is 75%, because each of these years it has a certain probability of default. And note one thing, the probability that it defaults between year 1 and year 2 is smaller than 7%. And the probability that it defaults between years 2 and 3 is about 60.5%. Okay. The reason is that, of course, the bond could default at many other times, so the probabilities gets smaller over time. Now, these probabilities are done. We know them. They come from in the case of 8 default states, they will all come from the different powers of the Markov transition probability matrix. We know all of these numbers. They are given to us. They are part of our database. Okay? No problem with this. We know this. Great. So now, the first thing I'm going to do is I'm going to calculate the expected loss. And then I'll go to the unexpected loss. The expected loss, there's 2 ways of calculating the expected loss. I'll do the easiest one, which is calculating the expected cash flows first, and then taking the difference. So I have 2 cash flows, $5 at time 2 and 4. And I know the probabilities of default at each of those times. The probability of no default, the probability of solvency was in the previous database. I don't have to bring it up again. And the probability of no default in year 4 was 75% or something. I don't have to bring it up again. So the actual answer is $8.06.5. These are the expected cash flows, or in the language that we developed last week, the expected cash flows from this series of 2 payments. That translates into the expected loss to be 1.935. We expect to lose about $2 on this trade. And the expected cash flows are about $8.06.5. So let me ask a question now to Chris and Daniel. How much would you pay for this bond? Let's say we do an auction between the 2 of you. It's a mock option. It's a mock auction, okay? But how much money would you offer? Give me a number. Daniel and Chris. Everybody else watch. these two experienced traders, how they auction, how much money. Can you see the conditions on the first page again? Yeah, the conditions is there's nothing special. The conditions is what you expect. It's a bond. It pays two $5 coupons. It pays two $5 coupons. 7% probability of default. This we're going to ignore for now. Okay, we'll bring this later. Don't look at this now. This will affect your thinking. We don't want this right now. I'll bring it to $7. Daniel will offer $7 for this. How about Chris? How about Chris? If Chris doesn't offer anything, I'll give it to Daniel. $6. Okay, so Daniel is yours. You pay 6. You pay 7. Chris pays 6. Okay. And by the way, you will see later how interesting this trade is. There's something very entertaining in the two answers you gave me. Okay, thank you for that. You will see. You will see. Okay, great. So let me continue. I have so the bond is sold to Daniel for $7, and Chris, you're not. Well, it's Daniel's. Unless you want to change your bid. I mean, I give you no. You don't want to change your bid. No. See, let me tell you one way of thinking about this. One way of thinking about this would be the expected cash flows are 8. Daniel is being very smart, offering 7, so he keeps 1 to himself, and 2 he expects to lose anyway, right? So he thinks that $1 expected profit for this transaction is good. And everybody remember that now we are trading for money. We're not trading just to break even, okay? That was in the first half of the course. And I can see that Chris is much more risk averse. He says, no way, I don't like this bond. Something bad is going to happen with this. This is too much risk for me. I just don't want to take it. So he offers 6. So the bond goes to Daniel. So Chris, your last chance. You want to offer 7.5 maybe, or no, you stay with 6, no? This is how an auction works. You stay with 6. Okay, great. Okay, Daniel, the bond is yours. Great, thank you. But now let's do the following. So the first thing I want to do is I want to calculate the expected cash flows in a different way, which I do it just for mathematical reasons. And what I can do is I can calculate the exposure every year. The first 2 years, the exposure is 10. After year 2, the exposure is 5. Why? Because I already received the first $5 coupon payment in year 3. So the exposure is 5. All I can lose is the last $5 payment. So this is how you calculate exposures. In this case, it's very clear how the exposure equation changes. I like this example because the exposure calculation is very clear. Yeah? And by the way, you could multiply the probability of default or solvency in those years by the exposures, and you're going to get exactly the same result as we obtained earlier for the expected cash flows or the expected credit loss. It's right here. Okay, all right, that's fine. I don't care about this. We're getting the same number anyway. And I have 2 bids, one for $8 and one for $7, one for $6. The bond goes to the highest bidder, and that's $7. Great. Okay, perfect. Now let me do a calculation now. I'm going to calculate the unexpected loss. It may not be clear why I'm doing this. It'll become clear maybe later. So let me do the calculation of the unexpected loss. And for that, what I do is every year 1 and 2, 2, 3, 3, 4, what I'm going to do is I'm going to calculate the standard deviation of losses. In this case, what I'm doing here in this page is the variance of the losses. Okay, the variance of the losses is here. In the next page, I'll take the square root. Okay, but this is the part where everybody knows the square root. I don't want to stress the square root taking part of this exercise. I want to emphasize the variance calculation part of this exercise. So is this clear? Is this clear? Okay, it should be clear. It's clear. I declare that everybody understands this, okay? I don't have a question in the chat, so everybody understands this. Very good. Now here comes, why are we doing this? Who cares about these numbers? Who cares about the unexpected loss? Who cares about the unexpected loss? Well, math professors care about the unexpected loss, but that we don't care. We don't care about math professors right now. Okay? In the industry, who cares about unexpected loss and why? So the one person who cares about unexpected loss is Daniel. Daniel works in a bank, not Silicon Valley. He works in a bank, and say, well, look, if something bad happens, and the bank is taking risk. When Daniel trades this bond, the one who's taking risk is not Daniel, it's the bank. So the question is, how does the bank react to the risk that Daniel is taking? And not only the bank, how do the regulators of the bank react to the risk that Daniel is taking? They're going to react by doing a risk calculation, which I'm about to show you. And this risk calculation is going to lead to a capital charge to Daniel's profit and loss function, to Daniel's book. Daniel has a book. Daniel has a few, $1 million to trade, and he decided to use $7 of that to do this trade. So, because of that, the $7 trade that he's going to do, the bank is going to get some money from his P&L as a credit reserves, as we saw, and regulatory capital. You understand this? That's what banks do. And they still default, right? Does everybody understand this? This is how banks work. Good. Now, Chris is working for a hedge fund. So what does Chris do in terms of calculating the, unexpected loss or things like that? I don't know how much you know about hedge funds or banks, but this is a bit of a rhetorical question. Chris doesn't care about the unexpected loss. Chris has no central bank to report to. Maybe if this is a leveraged trade, the bank that is giving the leverage may not be happy with the level of risk that Chris is taking, but normally this is Chris's decision. He likes the risk or he doesn't like the risk. He has no regulatory supervision in terms of economic capital, credit reserves, or anything like that. He can do whatever he wants. He will have a chief risk officer in the hedge fund if he works for a large hedge fund, and then the chief risk officer may decide that he wants to do something fancy with his risk that he's taking. Let's assume that Chris works for a one-man run hedge fund, so it's just himself and his investors. He's supposed to look after his investors, but the investors are doing their own thing. They are on vacation in the Bahamas or something, so Chris is on his own. He can do whatever he wants. Everybody understands this? But Daniel cannot do whatever he wants. You guys, some of you will work in a bank, and you work in a bank, you cannot do what you want. Okay? And sometimes, even if you're the CEO of the bank, you cannot do whatever you want. Because even the CEO is subject to whatever the regulators say. Okay? So Chris doesn't care, but Daniel cares about this calculation I'm about to do. I'm going to do it now, and then I'll tell you the implications of this. Well, the implication to Chris is nothing, okay, but it's going to have implications for Daniel. The implications are as follows. Let me just go to the calculation, and this is what I have on when I take the square root. I'm gonna take the square root and multiply by 2. Why by 2? You know that if I multiply by 2, I end up having the 99th percentile of losses of the Gaussian distribution. So taking the square root multiplied by 2 is something that you see very often in risk calculations. That's what I'm going to do. Take the square root, multiply by 2, and that's the number I get. That means, so every year, and so Daniel is going to have a risk capital of $5 on year 1, $4.93 on year 2, and $2.38 between year 2 and 3, and $2.31 between years 3 and 4. Okay? Okay. So these are the numbers. This is the unexpected Everybody knows where the numbers come from? Everybody knows? Everybody knows? Okay, I guess so. This is 2 sigma per year. Okay, great. Now, so what about this? What about this? When Daniel sees these numbers, he's going to freak out. Because he's like, oh my God, $5? You're going to take $5 for a $7 trade? He's paying $7, okay? They're going to take, you get it back if there's no default, right? You paid $7, you have a pretty good idea you're going to lose $2 in this trade, but now they're taking $5 from you, which you will get back if there's no default. And then 4, and then finally goes down to 2, and then goes down to 2. The thing is this, and this is a true thing. You're going to take that money taken away. You have to send it to Ottawa. Okay, this money goes to Ottawa. It's not yours. And this introduces a very interesting economic consideration. Now I'm going to go back to the part that I said don't read. Now I need to explain this part to you. Okay. Now you're in a position to understand this. Now we can all understand this. We're going to assume that the default free party, so Daniel, maintains a risk capital to cover the standard deviation of losses that is adjusted. It is adjusted annually, and it depends a certain return on its risk capital. I haven't told you what the return is yet. But when Daniel works at a bank, when they say, I take this money away from you, the money that Daniel is given to trade in the bank is not free. There we go. It's not free. Daniel has to pay some, it's not interest, it's called the return on capital on that. This number changes from bank to bank and job to job, okay? And I say, assume a 10% capital charge. I'll explain to you what this is. Let me tell you, 10% is very high. 5% is very normal. 2% is about right, okay? 10 is very high, but it's easy to multiply by 10%, so I keep 10%. And also it leads to a tremendous exaggeration, which is the point of this exercise. So when Daniel does this trade, this is what's going to happen. On the $5 he has to put aside on year 1, this is money he cannot trade. And he's going to be charged 51 cents on year 1 for that. This is an actual charge. Okay? Every time when they give you $1 million to trade, they're going to charge you 10%. $100,000 you're going to be charged, not you personally, obviously. The bank is going to take that from your P&L. Okay? Think of it as interest. It's not interest, but think of it as interest. You're going to lose, because you have $1 million, you're going to lose 10 million. That means that your performance at the end of the year and your bonus and everything will be calculated on what you make minus 10%. The bank is going to demand a 10% return on that money. I told you 10% is high, 5% is 4%, 3%, but it's easier to multiply by 10%. That's why I'm picking 10%. The concept is the same. Okay? So, so Daniel, you have an actual additional loss because of this, because you're in a bank. Okay, and that loss is 51 cents in year 1, and 49 cents in year 2, and 23 cents in year 4, and 23 cents in year 4. 1, 2, 3, 4. Okay, that adds up to a charge altogether of a loss of $1.47 because of regulatory charges. Okay. Now, this is important. This is important. I'm going to stay with Daniel. Daniel has the interesting job here. Actually, it's the job that most of you are going to have. Very few of you will be as lucky as Chris that you can do whatever you want, right? And then actually be paid a lot of money if you actually get it right. So let's see. Let's do a calculation. So Daniel is going to lose about $2 as expected credit loss plus $1.47 as regulatory charges. So Daniel is going to lose $3.47. That means that Daniel will not want to pay more than $6.50 for this. You offered 7. You didn't know this. Okay, you offered 7, so you ended up losing 50 cents. And losing as an employee. Okay, I mean, sorry, and again, you don't pay the 50 cents from your salary. It just comes from your P&L. Okay, but that's the fact that you're part of a bank. So Daniel would not pay more than $6.50. Chris, on the other hand, Chris, are you willing to change your bid now? No, you still stick with 6. Eh? So you actually gave it. The funny thing is that you gave the bid that a bank would give, Chris, and Daniel gave the bid that a hedge fund would give. This is interesting. And Chris, you're absolutely. That's exactly what you would do. And this is how people that run hedge funds trade. They know how much the banks can charge, because they know how. Most people working in hedge funds, they've been working at a bank for many years. They know how it works. They know at what point JP Morgan cannot show up and compete with their bids. You understand this? This is very, very important. Everybody needs to understand this example. It's the most important thing we will learn today. There's no math here. I want you to understand how credit trades work, how banks charge capital, risk capital to your traders, how hedge funds are free from that, and how competition happens. When this bond is out there, everybody thinks it's a good deal, okay, at some price, obviously. Hedge funds have the advantage over banks that they're unregulated. They can offer whatever amount of money they want, okay? Chris has another advantage that probably worked in a bank for 20 years, so he knows exactly how much money Daniel can offer. He knows exactly at what point Daniel will say, I cannot do this, I'll lose money. And that's why Chris will know that he can do this deal, not for $7, as Daniel said, maybe even for 6.6. All right, everybody tells me whether you understood this. If this is not understood, I'm not moving on. Please write in the chat yes or no. Yes, you understood. No, you didn't. Very important example. Very important example. I only got 2 answers. Where is everybody else? Nicola understood. Susan understood. Okay. Daniel understood. Great. I'll give you a lot of examples from now to the end of the course. Real examples like this. Real examples like this. This is one of the most interesting ones because this is how you understand how banks work and how hedge funds work. We're going to spend a whole day talking about hedge funds. Still, this comparison between banks and hedge funds, I will not be able to do there. I'll do it here. I may refer to this example later, but this is something which is very, okay, so everybody understands as far as I can tell. That's great. Don't forget this example, okay? And when you have a job at a bank, go back to this example and remember how it works. It'll help you. Great, okay. So this is good. I'm now going to rush because what I have to do next is, it's important, it's not as important as this. And I'm going to touch on many things that you already know, and I'm going to rush because I don't want to go over time. Oh, and I have a few things that I want to cover. This is the high point. I didn't want to rush to get to this. And by the way, thank you very much, Daniel and Chris. I'll send the bonus your way for participating in this trade. Okay. Yeah. Class participation matters. You know. Okay, great. So that's your bonus. Perfect. Okay, great. So now I'm going to continue then, and the next thing that I'm going to do is I don't know if I want to do this. Like I told you, I'm going to rush now. You're still free to stop me if something is particularly interesting to you. But what I have now is I'm going downhill from here, and you can always go back and look at these things again and so on and so forth. Okay, so credit VAR, we already saw, it's a quantile function. Okay, there's not much else to do there. And then there's examples. I have one example here. I'm not even going to read it to you, but it's an example which it gives you, credit VAR with a ridiculous confidence interval of 0.1%. And then it gives you some bond value and then blah, blah, blah. And then you're asked to calculate the credit VAR. Well, you have to do, this is a problem in probability. Once you understand the English, it's a problem in probability. And then you just do it. Big deal. It's here. no problem. Here's another one, something similar. This case, I have two bonds, still a ridiculous confidence interval. It's an exercise in probability, which is a bit more complicated. That's the answer. You do that if you have to. This is something which is it's done. Okay, fine. Done. Now, this is more interesting, which is two credit models that exist out there. The first is the credit matrix, which I will do with some care, and then the KMB, which is based on the Merkel model, in which I will focus on essentially the miracle that will happen. That's when the miracle that I announced last week will actually happen. So credit matrix is one that was done by JP Morgan, and it is based on the credit model that we saw last week. Markov transition probability matrix, credit ratings. But a credit event is not only a default. A downgrade or an upgrade is a default event. You can make money on an upgrade and you can lose money on a downgrade. So this is something which is a little bit more, the distribution is now, is still asymmetric, but it's not as asymmetric as before. You can actually make money on an upgrade. Here we can actually make money on a credit event. Okay, but it does not integrate market and credit risk. It's very difficult to do that, and not this model. Of course, when you make this in practice, you integrate market and credit risk, and as you will see, the mathematics this gives rise to is so complicated that you typically need special purpose companies that actually solve this for you. The obstruction to making this model work is a mathematical obstruction, 100% mathematical. You will see. Okay, 100% mathematical. And that's why this is interesting for you. So this is how it works. I have an example here. I have a bond, triple B, and S&Ps give me through the transition probability matrix how this bond could transition to different credit ratings in a year, and gives me the value of this bond in a year. The value is only taking credit into account, not market into account. You know, bonds could go, so rates could go through the roof and then this bond could plummet. They don't look into that. This is strictly a credit model. Okay, you want to take into account the value of interest rates, then that's not credit matrix, that's something else. Okay, so then with that, you can do statistics. That's the expectation and that's the standard deviation. Great, got it. So with that, I can get my 99% credit value at risk, or I can get my 2 times standard deviation. Up to you. And we can see that the credit value at risk is higher than 2 times the standard deviation. We expected that. I told you that for fat tail distributions, 2 times the standard deviation will underestimate the 99% quantile. And you can see that very clearly here. $6 is smaller than either 11 or 24 cents. I say 11 or 24 because the quantile function is somewhere, it's somewhere there. So actually not there, no, it's somewhere here. Somewhere there, okay? All right, great. That's easy, that's no problem. But now what happens if you have more than one counterparty? So credit matrix for one counterparty is very simple. It's probability theory like you saw when you were babies, nothing, okay? The problem is, how do you do this with several counterparties? If the counterparties are uncorrelated, it's kind of easy. Goes back to the examples we did earlier. But if the counterparties are correlated, this is going to be a little bit challenging. And this is what I want to tell you. This is how they do it, okay? This is how, I have an example here. I want to explain this through an example. And I'm going to take 2 companies. One is DuPont and the other one is Allianz. Allianz is a German insurance company. At the time I did this, they owned a bank. Dresdner Bank was property of Allianz. And DuPont is a plastics manufacturer in the United States. So the way you're supposed to do this is, and this is a recipe, okay? There is no, I cannot tell you mathematically why this works. This is the recipe that Credit Matrix says you have to use. Credit Matrix gives you a whole bunch of matrices, which I will explain, and a whole bunch of time series, which I will explain. So for DuPont and Allianz, you get their stock price and daily stock return. So you create the stock return time series for each of them. And then you regress them against some indices which are given to you by credit matrix. One index happens to be the U.S. Chemical Industries Index, to which DuPont has a beta of 0.9 and a certain error. Forget about the R squared. This is a recipe, so we don't need R squares. And this is not surprising, right? DuPont is a chemical company, so there you go. Yeah, that's what we expect. Then I do the same thing for Allianz. I'll do it in blue because the logo of Allianz is blue. And for Allianz, what you see is that when you do the regression, you get a beta of 74% to the German insurance index and a beta of 10% to the German banking index. I told you they own a bank. Great. And this, we don't care. These are just errors. We throw them away. Now, the recipe that Credit Matrix says you should do is as follows. Is multiply these two expressions, and the correlation of default between these two is going to be the product of the betas times the correlation of default between these indices, which of course does not make any sense because the indices do not default. The correlation of default between the indices is a matrix given to you by Credit Matrix. You buy it and it's yours. So as you can see, you can calculate the correlation between two counterparties as a matrix multiplication of certain numbers given to you and certain betas which you calculate in linear regression. Is that clear? I'm saying not if you understand why. No one understands why. Is it clear as a recipe? Yeah, I guess. Okay. Can you show an example of what matrices you are multiplying? No, I can't because I'm not a client of Credit Matrix. So these are matrices which are given to you. So basically okay, think of it this way. If you're going to calculate the correlation between these two random variables, these random variables are expressed as betas times these other random variables, right? So the correlation between these two random variables is a function of the correlation between these two random variables times betas, right? And what I can tell you is that those matrices you need to finish this calculation are given to you by Credit Matrix. That's all I can tell you. I don't have the matrices. I could make it up. I have the answer to this question, by the way. The answer is here, right? So this is the correlation between these. Maybe this is good enough for you, and then that. So the question is, what is this and what is that? I say, I don't know. Ask Credit Matrix, and then they say the answer is some number, and then great, you multiply, you get 11%. These are given. Again, these things, yes, exactly. You are multiplying matrices of credit correlation, which are given. But see, I have to say they are not really credit correlation matrices. They are implied credit correlation matrices or something like that because indices do not default, right? They're just numbers given to you by Credit Matrix so that this recipe works. This recipe does not work unless you have those numbers. Those numbers don't exist, so they give them to you, and now you have them. Okay? Great. Now this gives us the correlations. That's great. Are we done? No, we're not done. We have barely started because what we now need to do is this. This is the second part of the recipe. You have say 1,000 counterparties, 1,000,000 counterparties. This is what you do. You can calculate the massive correlation matrix in this manner, no problem. We have the information about the marginals. We obtain that here. This is the marginal distribution. We have that. We have the marginal distributions and the correlations. How do you put them together? All right, so you're going to put them together through a simulation mechanism. What you're going to do is you're going to simulate. You have m counterparties and n possible credit states. So actually, this is wrong. This is n to the power m. Okay, so you have n to the power m possible situations for your counterparties. You know the correlations, so you can simulate. Remember that we already did this with the two correlated coins when we're looking at the commercial mortgage example. We knew the correlations, so we could get the joint probabilities. So you get the joint probabilities, you can simulate this beast, And when you simulate the beast, what you do is you replace this exercise we did here, here for one counterparty with a simulation of many other counterparties, because we will know the value of all of this, and these probabilities, which are marginal, will be replaced by the joint probabilities. That's how it works, simulation based. Okay. Now there is this is what Monte Carlo does for you, and here you can introduce copulas and this and that. This is a whole industry. Okay, I could teach an entire course on just how to do this. So I just want you to know that there's a massive simulation exercise to be done here. I'm not going to explain it anymore. It's less interesting for this course than to understand the context in which this thing is done. And note one thing, that the total number of simulations here is n to the power m. Again, this is a mistake. So, which, let's say for a typical bank, there will be 8 credit stage for your counterparties and maybe 1 million counterparties. That's what you're doing. This is huge. Okay. Of course, this is huge, doesn't mean that it cannot be done. There's a lot of mathematics built into this. When people talk about big data, this is big data. There's a lot of mathematics that you can use to do a simulation in space of such high dimensions, because in this space of such high dimensions, most directions don't matter, okay? And so there is a way to do importance sampling, principal component analysis, and this and that, which are mathematical theories to turn some problem which is impossible into a problem which is possible. Here the challenge is to go from impossible down to possible. Note that these numbers you have to do in less than 24 hours, right? So that's credit matrix. I don't think I want to say anything more about that. You get enough understanding of that? Yes, I assume. Okay. Because now I want to do the Merton model. That's commercially less important, academically more interesting. And at the end of today, you will know both. You will know enough things about both for what I think most purposes will be. Now, and the correlation factor is obtained by... Yes, that's right. You're right, Chris. I just read your chat now. Okay, Chris, you're right. Great. So let me move to the next topic. And there's something very, very important, a historical fact here that I need to emphasize. This is perhaps the most important aspect of the whole thing, which is how did this thing happen historically? It's very interesting. What happened is this, that Fisher-Black and Myron-Scholes did their Black-Scholes theory in 1973. I'm not sure if I told you that when they did that, Robert Merton was working on the same problem, which he solved differently a few months after Myron and Fisher-Black. And his method was different. And the interesting thing is that when the Black-Scholes theory was established, either the Black-Scholes way or the Merton way, what happened is that Merton did a very nice application of that theory, which is what we're talking about today. And what he said is this: when you have a company, companies, as we discussed I think last week, they're structured with a limited liability characteristic. There's an aspect of companies in the developed economies which is they are limited liability corporations. That means that they can default. Okay, it's something that you get for when you create a company. You can default. Great. So Merton's view was, if they can default, that ability to default is worth something. And how much is that worth? That's the question. How much is that worth? And this is why, one of the reasons he needed to have the Black-Scholes theory, which actually people call it a Black-Scholes theory. People who are more history aware, they call it the Black-Scholes-Merton theory. So Merton's contribution to this theory was that companies can default. There is value embedded in that. And in fact, he said the shareholder structure and the bond structure of a company is as follows. So I'm going to explain that to you. This is what Merton did the minute the Black-Scholes theory was established. Okay, so it was done so fast that I suspect this is the reason he wanted the Black-Scholes theory or Black-Scholes-Merton theory. So let's listen to this. Okay, pay attention. This is important. A company, what is a company? A company is a legal entity that has assets and liabilities. And as you know, if you've done accounting, the equity is the difference between the value of the assets minus the value of the liabilities. Okay, great. So I have here the graph of, that's 0 right there, 0. And then the value of the firm would be, you have certain assets, and some of that would be debt, okay? And when the value of the asset is above the value of the debt, right there is when the equity is worth something. So at this point, the equity is worth nothing. The value of the assets is equal to the value of the liabilities. Any time that the value of the assets is bigger than the value of the debt, this is dollars that go to the equity holders. And every time that you're here, then you're in a technical default, and then the bond holders are entitled to whatever the assets are worth. The equity shareholders are worth nothing. So all through here, the value of the equity is 0. And all through here, the value of the equity is the value of the assets, which are called V, minus the value of the liabilities. Liabilities are called K. Okay? But this should be very familiar, because we can put both answers, 0 here and V minus K there, in one language, which is to say that the value of the equity is V minus K, positive part, right? In other words, what Merton is telling us is that the equity is a call option on the value of the assets of the firm, with the strike price given by the value of the liability. Understand that? It's as if the shareholders can say, oh, well, this is my company. Let me see how much they have. Let's see how much they owe. Oh my God, they owe a lot of money and they don't have that many assets. Then they say, well, then I default, I leave that company on its own devices, and then I just move on, right? That's one perspective. That's one perspective. But if they say, oh no, look, the company is worth a lot of money, and then so I keep it, I give the money to the bond holders, and then I keep the rest. That's exactly what an option was. Except up until today, we always considered options on stocks or traded instruments. Today, for the first time, we're considering options on untraded instruments, options on assets. A company owns, Apple, what does Apple own? They own patents, they own factories, they own probably some iPhones, I guess, okay. That's the value of all of those assets have a certain value. And they owe money. Well, how much money do they owe? Probably not very much. Okay, so from that example, Apple is not a very good example. But most companies have debt. So the difference of that is the equity. So this is groundbreaking, because the equity turns out to be a call option on the assets. Footnote: this would make a call option on the equity a call option on a call option on the assets. In other words, we'll make a call option on the equity a second derivative. Just a footnote. I don't want to get into that too much, okay? But let's take this and let's move on, because now this is very interesting. That means that the value of a firm is that, okay, has a certain payoff. It's not clear at what time this payoff is there. Is this a perpetual option? Is this an American? What is this? I'm not going to get into that. Again, I want to now go quickly through that. I'm not interested in answering all of these questions right now. This is perhaps more important for us, because the bond is the value of the assets minus the value of the equity. In other words, it's the minimum value of the assets and the strike price. Okay, if the assets are more than the strike price, then you get the strike price. If the assets are less than the strike price, well, take the assets, because that's your recovery rate. And you see, this model already has built in a stochastic recovery rate. The value of the bond, the recovery, is here, right there in front of your eyes. Of course, I'm doing an example with a single counterparty in the capital structure of the firm. We already saw that the senior secured, senior unsecured. And again, I don't want to do this theory with at that level of granularity. I told you I want to rush through this. I just want to give you some highlights of this theory. And that's all. That's all we need to know. But one consequence of this is that a stock is a call option and a bond is a short put option. And it's very clear here. That's it. These are the payoffs of a call and a short put. That's interesting because a call option, as we know, is worth more than VT minus K. So that's the value of the ability to default. It's the value of an option, which you could add to the accounting statements of a firm. No one does it. Well, usually no one does it. But that is the value of the firm being able to default. That increases the value of the firm, and it is how that protection makes companies valuable. All right, some corollaries of that. Let me just move on. Let's apply the Black-Scholes theory to this, right? After all, that's why Merton did the Black-Scholes theory, the Black-Scholes-Merton theory. So if I assume the value of the evolution of my assets is given by geometric Brownian motion, just as we did for the Black-Scholes theory, then what I have is the value of my assets is bonds plus stocks. Here I'm assuming for a brief moment no transaction costs, including bankruptcy costs. And then what we do is we invoke the formula from the Black-Scholes theory for a call option. The formula of the Black-Scholes theory for a call option, I gave it to you very quickly also. I was not interested in it. I have it here also very quickly. I'm not interested in it, except to point out a few things. When you go through those details, there are some elements that come into the valuation. This is the Gaussian cumulative distribution function, that one. And these numbers here, these little numbers here, they correspond to these quantities on which we apply the Gaussian. What's interesting is that when you apply the Black-Scholes theory in this context, these numbers are this, which is what? This is the liability discounted to today's value. That's the present value of the liabilities. And what is V? V is the value of the assets of the firm. So this is the leverage. This is called the leverage of the company. How much money are they borrowing relative to how much money they own? And then you notice that the volatility appears multiplied by the square root of time. That's the volatility at the period of time when I claim my Merton model will give me the right valuation for the company. Typically people take a year, but you can take longer, okay? Great. So this is good. Now I have to make one comment, which is in the Black-Scholes theory, we need the sigma. What is the sigma? Is the volatility of the assets. How do we know the volatility of the assets? How do we calculate the volatility of the assets? We don't know. We don't have enough data to calculate the volatility of the assets. For the volatility of the assets, we need a time series. And we don't have a time series. Oh, well, you can go to the financial statements of the firm, but they're done, what, once a year? Not enough. And Merton also addresses that in a very elegant way, because he says, well, using Ito's formula, what I have is the stochastic movement of the stock price, which I do observe is in the stock market, is related to the stochastic movement of asset prices, which I don't observe, times this ratio, times this hedge ratio. So that means that the stochastic part of the Ito process for ds will be equal to the stochastic part of the Ito process for dv with this multiplication factor here. And that is written as follows. This expression that I have here, is the one that says what the volatility of the assets should be. But note one thing, this is not a formula. This is not a formula. It's not a formula because both the right-hand side as well as the left-hand side are functions of the volatility of the assets, both. Right? Everything here is a function So sigma S is a function of sigma V. V is a function of sigma V. Everything is a function of sigma V. So this is not an equation, or if you want, it's not an explicit equation. If you want, it's an implicit equation. It's an implicit equation. See that? And moreover, it's an implicit equation which happens to be a fixed point because this thing is a sigma V. So you take this as a function of sigma V. Sigma V is the result of a fixed point of that transformation, which is the way we will find it in practice. We're going to establish an iterative method that will calculate these numbers for us, and they will give rise to the volatility of the assets as the solution to a fixed point problem. So we'll just leave it there and say, well, it can be solved. Let me continue with, that's not credit risk, that is something else. That's a computational element to all of this. I'll deal with that a little bit later. And because I told you I was going to rush, I want to rush to the miracles, and then we'll end it there. And the result is this, that if I apply the Black-Scholes theory with those numbers there, this is the value I have for the Black-Scholes theory, right there. Okay? This is the Black-Scholes theory for the bond, not for the call option. This is for the bond, which is a different option. And then if I rewrite that this way, if I divide in both sides of this expression here by that, what I get is this. That's what I get. And this is miracle number one. Why is this miracle number one? Let's look at this part of the equation, just this. What is this? That's the value of the bond. And that's the value of the bond without default, the riskless value of the bond. Okay? That's the riskless value of the bond. Great. What is that? According to the Black-Scholes theory, this is a cumulative distribution function that measures the probability of exercising the call. Or in other words, the probability that the bond will not default. So what we have here is that the probability that the bond will not default, this is that, which happens to be what? Happens to be the exponential of the credit spread. We call it H, right? That was H. We call it H. But remember, this is exactly the formula that we saw on day one, last week. We did it discounting cash flows, and now it's coming to us as a consequence of the Black-Scholes theory. In principle, no relationship, but we get the same formula. With the added bonus that, what is this? What is this? Well, this is because the Merton model has this stochastic recovery rate model built into it. As we saw in last week in the case of the sovereign default, we have to modify the relationship between the hazard rate and the probability of default by taking into account the recovery rate. But last week we were forced to do that with a fixed recovery. If the recovery was stochastic, we didn't know what to do. Well, Merton knows what to do, and this is the formula. It's here. In all of its splendor, everything is here, taking everything into account. So it's like what we did last week, but better. You see that? Okay, that's miracle number one. Miracle number two is here. If I do the calculation for the expected credit loss, what I get is, well, again, a Black-Scholes type function. Let me clean it up a little bit. Let me just go to the end. And what I have is this element here, that element there, and that correction. So morally, what this is the probability of a default, which is that, the exposure, which is that, and a correction from the recovery rate, as before. Miracle number two. What we did earlier in class today is given to us again by the Merton model. Okay. So this is miracle number one, miracle number two. My mission has been accomplished. This is what I want you to see. But let me tell you now that this model has tremendous advantages and disadvantages, but it's calculated in a very simple way, which is there's a firm created by Vasicek and some others that made a commercial implementation of this, which is very simple. The commercial implementation is as follows. A company with certain valuation will default when the value of the assets is below the value of the liabilities at a future point in time. So you can use geometric Brownian motion considerations to calculate what that probability is going to be. This is a formula where the distance to default is that's the distance to default, okay, distance to default. And then you apply the cumulative distribution function to that distance to default, and the result will be the probability of default of that company. This is a model which is very different from what we saw earlier. It is a Markovian model, but the probability of default is variable, okay, it's time dependent. And it's done very easily. You just look at the assets, look at the liabilities, and you calculate the distance to default, and then you apply the Gaussian to it, and you get a number. And you can do this as a function of time. Great. Now you can do assignment number 2, because this is what you need to do for assignment number 2. I'll write it down for you. But with such a simple approach, you can calculate this as a function of time. You do have to take that company that you analyze, and you do have to calculate, you have to check what their assets and liabilities are. You have to go into their financial statements, which are public, and you have to look for that number. You have to read their financial statements. And you're going to apply the Merton model, and you're going to apply the credit matrix, the Markov model with their credit rating, okay? And you're going to use the hazard rate observed, the credit rate observed, to calculate the probability of default, as we did last week and earlier today. That's your assignment number 2. You're gonna have to pick a company and do this analysis. Don't write it down yet, because how you write it down, I will explain in a week or 2. But you can start now that exercise. Pick a company. Okay, if some of you wants to pick a Silicon Valley Bank, taking data from a week ago or something, just make sure you have it, and then yes, ask me, and I'll allow you to do that. Otherwise, pick a company that you can find the data either through the website where you get bond data or something like that. Okay, and then in the 5 minutes that remain, I have to tell you how to calculate the asset volatility, which you will need for this model. Okay, you see here the asset volatility. That's great. Where's that coming from? We don't know where that's coming from. I told you, we don't know. We know the stock volatility, but not the asset volatility. There was one equation, though. It was a fixed point that gave us the asset volatility. Forget this. And I have an example here how you do that. Let me just go here. Yeah, here we go. Okay. Oh, no, sorry. No, let me just go. These are exercises. Yeah, this is how I did the volatility, the asset volatility of the Goodrich Corporation. I calculated a whole bunch of numbers from their stock exchange, from the company's financials. The interest rate market is there. It's all good. And then what I did is as follows. I said, well, the value of the equity of the company is this. The value of the assets is that. The value of the debt is in the financial statements. So I get everything. Forget dividends. Don't do dividends, okay? Forget dividends in your analysis. So I have the present value of the future liabilities. I got that. And from that, what I do is I establish, this is the equation that I need to solve, is right here. And what I do is I pick I'm going to solve for a fixed point. How do you solve for a fixed point? I guess you know, right? Well, I guess you know. You may have seen fixed points in your earlier life. If you take a transformation t, a gradient is 0. I don't know what I mean, but I do this, and then that gives me an x1, right? And then I do t of x1, and that gives me x2. In other words, t to the power n of x0 converges to the fixed point. That's how you do it. So just iterate. You just iterate like that over and over and over again, right? So I did it here. I picked a certain volatility, 50%, and then I calculate all the numbers. V is everything, right? And I get a number for sigma V, which is what is it? Sigma V is the multiplication of that, which is 50%. And then S is here. S is the stock price, right? is the price. Don't forget, the price of the option is the equity. That's what we said. And then V is the value of the assets. So the value of the assets was, I get it from the company financials, and that's the delta of the option. The delta of the option is there. It's actually the inverse of the delta of the option. Is there. So I multiply everything. I get a number. I get 14. I get 14.7. 14.7 is not what I started with. I started with 50. But now I rerun everything with this new number. I got 14.77. And what do I get? I get that the multiplication of all of the new numbers I get here are exactly 14.77. So this converged in one iteration. This fixed point converged in one iteration. And that's how you get it. And I have 1 minute for questions. Okay, I'm done. The rest are examples and problems that you can do. I have 1 minute for questions. Probably not enough, but this gets you started in thinking. And next week will be, yes, class in person next week. And I will start class taking questions about this because this is your assignment number 2. I give you the highlights. This is a very extensive theory, but everything that you need for the assignment and everything I want you to know is already being highlighted. The rest is something which, as you become experts in this, they may become useful. For now, no. Okay. Okay, great. So we leave it here. Today we climbed a very tall mountain, a very, very, very tall mountain, and the last was very. No, the assignment is not posted yet. I'll post it. But start looking for a company. I'll post it, what you have to do. And I will be talking about this next week anyway. Okay? I'll start with this next week. In person, in Toronto. Okay, guys, so it's 2 p.m. Today was, you got a lot of exercise with me today. A lot of, hiking exercise. So I'll see you next week. Bye-bye.